Here we're going to take a look at waveform update rate. Waveform update rate in digital oscilloscopes has been a hot topic lately. Many manufacturers specifying extremely high update rates in excess of 1 million waveforms per second. One has to be careful with update rate specifications as stated on datasheets, however, because they're usually stated for certain circumstances, certain settings, and typically don't include things like measurements or mask testing that may be turned on when you're acquiring waveforms. So here we're going to take a look at the update rate of the Rohde-Schwarz RTO when it's actually doing a mask test. I think one of the more demanding type of measurements that you need to do on an oscilloscope. So we've got a demonstration board set up here with a data signal running, and the data signal, we're injecting errors into the signal at a rate of 1 per second. It's a particularly challenging type of measurement because a typical digital oscilloscope with the typical update rates that you see have a very hard time finding things that happen once per second. So here we're looking at the waveform. We're going to zoom in on the waveform, adjust the time per division settings so that we have an appropriate scale, and I'm going to set it to 100 or 10 nanoseconds per division on the horizontal scale. I'm going to turn off this this waveform bar here just so that we have a little bit more view of the screen. So now I want to adjust my trigger so I'm triggering both the rising and falling edges of this data signal. So I'm going to adjust the slope so that I'm looking at both slopes. Now you can see the 1 level, the transition, the 0 level. And I'm going to position that waveform so that the transition happens at the far left of the screen. I'm going to do one more adjustment of the time scale so I can get both transitions in. So now I've got my transition, my 1 or 0 level, and the next transition. Now, in a data stream, the signal should never go into this area on the screen. That would indicate a bit error, or a system could misread a 1 or a 0 as being the opposite value. So normally the way to test this is to put a compliance mask in that area to see if the signal travels into the mask. So we're going to set up a compliance mask by selecting the mask test tool. We're going to draw a mask on the screen by just selecting the vertex points of the mask. So now we're looking at the mask on the screen, very quick setup of a mask. I'm going to turn off that tool by touching out here. So now the gray mask indicates that the instrument is actually mask testing, and you saw that red flash when the error occurred. Now the other thing we'd like to know is exactly how fast is the screen updating. And one way to do that on the RTO is to select the performance display parameter. So we're going to turn on performance, and you can see the readout here in waveforms per second. And I'm going to try to make sure we maximize that. And do a couple of other adjustments on the display. We're going to display dots rather than drawing a vector between the waveforms so that we can see the fastest update rate on the screen. Now, if you look in here, if we can zoom in on that number, you can see that the update rate is about 640,000 waveforms per second. This is significant because we're able to acquire 640,000 waveform measurements per second at the same time we're doing a mask test. We achieve this speed by building into a custom ASIC on the oscilloscope the mask test measurement. And so we can do this at extremely high speed. Now for the mask test, I'm going to set up the mask test so that it stops when an error occurs. So I'm going to go into this setup. I'm going to set up events, actions, and on my stop acquisition, I'm going to select stop on violation. And I'm going to wait for an error to occur. Now on average, it should take 30 to 40 seconds for one of these errors to occur because they're happening at once per second, and our update rate is 600,000 per second. Notice when we've caught an error, the instrument stopped, the mask turned red. Now that we've found the error, I can use my history control to scroll back through the memory and see the specific waveform that caused that mask failure. So press the history button, and I'll dial back in through memory, and here you can see a passing waveform, and then as I turn there, you can see the error occurs right here where the signal amplitude drops into the mask before reaching its final value. This is an asynchronous error that was added into the data stream, and we were able to find it in less than 30 seconds on an error rate of 1 per second. Typical oscilloscopes doing mask testing would take minutes to maybe even hours to find this type of an error.